Beautiful. Well, first off, just want to say thank you to the Aging Initiative for having me here. Really great group that you guys got here. And lots of familiar faces in the audience. Also, thank you to the rest of the panelists. I think what I'm going to be talking about is, in some ways, completely different, and in some ways, exactly on the same lines as the goal of Until, fundamentally, is to build a consequence. Scientists and engineers, that a great lever to pull here is temperature, right? Metabolism, chemistry itself, these are exponential functions of temperature. And so if I give my biology very cold, then I can arbitrarily dilate my biological time. Now, we also know, as scientists and engineers, and people put things in freezers, that once you get around 0 C, something really interesting happens to something that's sort of first order bag of water, right? You have your water molecules go down, you get to form a hydrogen bond, ice will form, this expands in volume relative to liquid water because ice is less dense, and you begin to tear up cells and tissue. However, there is a magical fact that makes the entire operation possible, and it's this. There is a temperature too cold for ice to form. So imagine now, if I can cool quickly enough to get through the temperature regime where ice typically forms, I get to a point in which now it is too cold for water molecules to rearrange one surface. And instead of phase transitioning from liquid water to crystal ice, I phase transition from liquid water to a glass. And when I say glass, I literally mean like the glass that is in the back of this room, where you drink the water right out of. Glass, and I didn't appreciate this before the company, is closer to this sort of amorphous fluid that flows on geologic timescales than it is to a normal crystalline solid. And it turns out that if I can turn it into a glass at very cold temperatures, things move very, very slowly. In the glassy state, it will take millions and millions of years for a water molecule to diffuse the same distance it does in 1 second at 37 C, where we are. And so if you want to dilate biological time, this feels like a very good strategy. However, you may say, John, like this sounds like a cool physics concept, but can this actually be useful? And my answer to that would be yes. Actually, in the span of me giving this presentation, a baby has been born in the US because of this phenomenon. Right? In vitro fertilization, IVF. You take an embryo, you put it in a straw, you dunk in liquid nitrogen. Because it is so small, heat transfer is exquisite, and you instantaneously undergo this glaciation. And Molly here, very cutely, actually holds the record for being cryopreserved for 27 years before being implanted. But frankly, Molly could have been in cryopreserved state for 2,700 years. Right? In this vitrified state, nothing is going to happen. Right? Things move on geological timescales. And so we actually utilize this all the time in the clinic today. And in a funny way, you can sort of summarize the technical challenge of Until as physically scaling up the technology of IVF. But it turns out that this is a little tricky. There's two main challenges when I want to take some biological sample and scale up this vitrification process. The first is just speed. Right? If I have a bigger object, the length that heat has to diffuse through is longer, and so it takes more time. And it turns out that if I just took pure water and I asked any of you to vitrify it, you would have to cool it at thousands of degrees Celsius per minute. Right? This is like prohibitively. So the first challenge, we need to figure out how to do this quickly at large scales. The second challenge is uniformity. Right? Like maybe I ask Satvik, can you cool down this kidney? Right? And Satvik is like, John, I'm going to dunk it in liquid nitrogen. Right? That should cool pretty quickly. But if Satvik were to do this, he would see the same fate as anyone who throws hot water on an icy windshield. You get cracks. You get this thermal gradient that builds up, differential thermal expansion, that causes mechanical stress, and this breaks. And so we're sort of facing these two challenges, right? I want to get my biology in this vitrified state. If I can get there, nothing will happen on geological timescales. But biology is mostly water, and water, thankfully for us at 37C, has both a high specific heat capacity and low thermal conductivity. And so doing this for large biological samples is extremely challenging. Thankfully, we've got some arrows in the quiver. And we've known for many decades now about a class of compounds that even when added in small concentrations to biological samples, will be very effective at arresting ice formation, right? Sort of antifreeze compounds. We call these cryoprotectant agents. And when you add these CPAs, the rates now that you need to cool and then rewarm your biological sample at gets significantly reduced. Right? So now instead of saying I need to cool something at thousands of degrees Celsius per minute, we can get to single degree Celsius per minute, or fractions of a degree per minute. And so this problem becomes substantially more tractable. Now, of course, anyone who's worked with Celsius before knows that if you add anything in high enough concentration to a biological sample, you're going to damage it. Right? If it's high concentration, you're going to get osmotic shock. Not to mention that a lot of the cryoprotectants, or antifreeze molecules, that the field has historically used, are toxic in concentration. Like think of like sort of sugar compounds, alcohols, right, GMSO, glycerol, these sorts of things. If you add these in high concentrations, you'll make it very easy to vitrify, but then of course it's toxic to biology. And so now we sort of have a high-level game plan for going about this. Right, we need to take our biological sample, we need to cool it and rewarm it quickly enough to avoid ice, down to this temperature where it's too cold for ice to form. We need to do this without adding too much cryoprotective agents that are toxic to our sample. And we also need to do this uniformly enough such that we can avoid damaging the tissue. And so now you probably ask, okay, John, this is cool, in theory, like where are we in the field right now? And thankfully, we stand on the shoulders of giants when this company started. The University of Minnesota, led by John Bischoff, has shown that not only can you cryopreserve a rat kidney and hold it for 100 days, although it could have been 100,000 years for all we care, in the vitrified state, but you can rewarm it, transplant it into a rat with no kidneys, and see that rat live a long, healthy life. Likewise, it's recently been shown that you can also do this on the scale of a rabbit, which is 10x larger than a rat. And so now you're moving, away from the regime of an embryo, which is like order single cell to tens of cells, to things that are getting closer to human scale. And we find ourselves at the frontier, right? Can we get to something that is on the sort of scale of a human side, principally a pig, for instance? And so this is sort of the frontier of where the field is today. Before I get into how until goes about trying to solve this problem, I want to first take a step back and try to motivate why exactly you want to build a talk about biology in the first place. I think there's two key reasons. The first reason is that 730,000 deaths in the U.S. annually can be attributed to end-stage organ disease. Over 100,000 people are on the waiting list for a donor organ at any given time. And to clarify too, these are like the sickest people, right? This isn't people who need an organ. You have hundreds of thousands of people on dialysis, for instance, and they're not on the waiting list. Multiple sources have estimated that if you had an adequate supply of healthy organs, you could prevent up to about a third of all deaths in the U.S. And these facts stand in stark contrast to the fact that over 50,000 organs that could be utilized each year in this country are tossed in the trash. Why is this? Right? If I'm an organ donor and I pass away, my organs are harvested, they're put on a bucket of ice. I've got anywhere between a few hours and tens of hours in the best case. What's going to happen in the best case is that that organ gets thrown on a private jet, and that private jet, if air traffic control isn't shut down, because the government shut down, or the runway isn't iced up, we'll try to find someone who needs that specific organ and has the sort of specific immune profile such that they'll be able to accept that. And the vast majority of the time, you can't do this enough. And so, and until we see this technology based on this idea of vitrification as taking time out of the equation, right? We see this sort of future in which the technology I described, you can take any donor organ, you can perfuse this cryoprotective agent formulation throughout the organ, as well as nanoparticles that will later be used for healing. You cool it down past this glass transition point. When it's in the vitrified state, again, millions of years can go by, and really nothing will happen to this organ. And at some point when you find a match, you can rewarm the organ, flush out the nanoparticles in the cryoprotective agent, restore health, viability to that organ, and ideally save a life. And so not only do we think that this is sort of the quickest way that we can deliver value to patients, but also a way that we can become a sustainable company and technically de-risk this technology at the same time. So I did say there were two reasons why you want to pursue this technology. This is the first. The second is admittedly more long-term, more ambitious. But I do think that if you're afraid of ambitious ideas, this is probably not the right time to do that. Without spoiling it, I want to tell a quick story first. The year's 1959, and a man walks into the Duke Medical Center in North Carolina. And he's lost over 20 pounds, he's had a headache for months, and his gait is staggering. The doctors quickly find out that he has a brain tumor in his brain. It's completely inoperable by sort of normal means. And they don't know what to do. And so the surgeons decide to try something that had never been tried before. What if we were to cut off the circulation in his brain such that there's a bloodless, motionless field, and we can actually perform the operation of this patient needs? Of course, you can try this, but a brain that's not getting oxygenated blood is going to be a dead brain very soon. That is, if you're at 37 degrees Celsius. What the surgeons tried that day for the first time was to cool the entire patient down to 4 degrees Celsius, exponentially arresting metabolism and buying them enough time to perform the operation that the patient actually needed. And that patient is like the thousands of patients today that undergoes deep hypothermic cardiac arrest for a variety of different surgeries. We ask the question, what happens in a limit that temperature approaches zero, and therefore time approaches infinity? Right? This idea seems strange and fantastical at first, but in the same way that I introduced the idea of vitrification alongside IVF, again, we do this all the time to a small extent. And so, not only that, but also nature to a small extent does this all across the animal kingdom. Right? We have animals like bears and hamsters that can go into hibernation, but also species that will literally go below 0 C for extended periods of time, finding out some way how to deal with or completely arrest ice formation, and wait out some long period of time. And until we ask the question, is this physically possible after you can do entire organs or entire organisms? And I think the exciting idea here is that if you are optimistic about the future of medical technology, you get to lasso that into the present. Right? In a way, you're solving the meta problem of medicine. Right? Can any patient today benefit from future medical technology? And so not only do we believe that this is technically tractable, but we believe this is socially important. And so we've been fortunate to raise over $100 million to date and assemble this exceptional team in order to tackle this problem. This is a difficult problem. I've been at the company for over 3 years now. It spans chemistry, biology, engineering, physics, surgery, you name it. We are working on it. We are not there yet, but I do want to highlight a few exciting milestones that we've been able to hit. That frankly, when I joined, I did not think was going to happen. Certainly at the pace that hit the map. For the first one, you may ask the question, John, okay, you are more than just your kidney. You are just your heart, your lungs, you are your brain, right? And anyone in the audience who's worked with neural tissue before knows how fragile it is. And so the idea of taking neural tissue down to liquid nitrogen temperature, right, almost minus 200 degrees Celsius, holding it there, bringing it back up, and seeing any sort of functional activity sounds like a bit of a farce. That's exactly what we did early last year. Acutely resected, eroded neural tissue. We were able to vitrify, hold, rewarm, and see action. And of course, you can say, John, okay, you can get functional activity, but that's not what really matters at the end of the day as well, right? You need more than just neurons firing. You care about the edges between those neurons. Right? You care about synaptic potentiation. And happy to share that in addition to sort of restoring functional activity in neural tissue, we, as well as collaborators in Germany, have been able to show synaptic potentiation is preserved throughout this cryopreservation process. And so while these are early results, we feel great confidence that this de-risks the long-term mission of the company, and we're extremely excited to continue pounding it as well. In addition to seeing these results in neural tissue, generally, if you want to preserve anything, right, you need very good cryopreservation, these anti-freeze compounds that I talked about before. I also said that the vast majority of the field that's used thus far are quite toxic. And so we've devoted significant resources in setting up a pipeline to explore basically the library of small polar molecules that exists. And I'm happy to share that we found multiple hits that we believe are both substantially less toxic than the state-of-the-art molecules that have been used up until this point, but also that these can vitrify very effectively. And so we think that this is extremely promising as we continue to expand, right? It's a great time in life to be alive and infer over large data sets, and we think we're just getting started. We think that this problem is substantially more tractable because this is the first time in history that we have the tools to be able to look over these large data sets in a way that we can. Finally, let's say you have good CPAs, you can vitrify well. Ultimately, I need to take a large sample and rewarm it extremely rapidly from the cryopreserved state. Naturally, there's interesting reasons why. It's much harder to rewarm than it is to cool a sample. And this has been the outstanding problem in the field for the last 4 decades. And so the kinds of systems that you need, frankly, don't exist. You cannot buy them. The closest thing that exists, sort of bespoke, one-off, $1 million device that takes up half the size of this room. It's 120 kilowatts of input power. You cannot put this in a hospital. I'm happy to announce that we've been able to make a system that beyond sort of being more powerful and allows for substantially faster heating of our systems is substantially more power efficient. And this is important because ultimately if you're going through revitrifications, you can't take 120 US households worth of power in order to turn the device on. Right? It has to be able to fit into a transplant center or hospital. These are a few things that I'm super proud to share. I think we are just getting started. I think it's a great privilege to work with people we love and respect on a problem that is hard, interesting, and important. I think this team has that in spades. It has been sort of one of the greatest pleasures in my life to see this team grow. And more than anything, as I close out this presentation, I want to say if you or somebody you know is ready for the next adventure, and this sounds interesting, please reach out. My email's up top, John at Labs, a few articles for open roles. But throughout the rest of the night, please come find me. Let's jam. If you have questions on science, I'll do my best to answer them. But thank you all for your attention, and I'm super excited to know.
Thank you so much, John, and thank you to all the wonderful talks we've had so far. I think this really puts into perspective just how far the field has come the past few years and how much forward momentum there is. So it's definitely a great time to be innovating, building in space. But here in this room we have probably around just over 100 people. And it's amazing to see the field grow, but the truth is, the field still remains quite small. And aging is a multifaceted problem. And to solve a multifaceted problem, you need a lot of different talents, bring together people from multifaceted disciplines. Which is why we're hosting FAR. The spirit of the Aging Initiative is to foster collaboration and innovation within the aging space in the Greater Boston area and beyond. And this event really brings this mission together. And you know, it's quite easy to say, like collaboration, ecosystem, innovation, and these are kind of almost buzzwords for the other day. They can often be quite hard to relate. But here in front of us today, even just the first speeches that we had, they really exemplify this vision. For example, you know, John Bailey, right, found his chief of staff for the aging mixer. And just yesterday I heard that BioAge was catalyzed by an aging mixer to be similar to this. So no pressure. But, anyway, I think now we're going to break out into networking. And you know, you don't have to start net BioAge quite yet, but I think you should try to meet someone, share your thoughts, share your ideas, and this is how we're going to move the aging space forward. So we've got food outside and we've got an hour, so yeah, go ahead.